In this lesson, we are going to look at how to use trigonometric substitution in order to evaluate integrals. This is really just a fancy form of U substitution involving trig functions. So let's think about right triangle trigonometry here for a moment. And we will label the sides of a right triangle as you see in the diagram here, where A is the length of the hypotenuse, and we have an angle theta, an opposite side U, and then adjacent side unknown. How can we write an expression to define U over A in terms of theta? So in terms of theta, U is the opposite side, A is the hypotenuse, so that would just be the sine of theta. U over A equals sine of theta. And then rearranging terms, if we multiply both sides by A, we get U equals A times the sine of theta. Now I want you to consider the expression square root of A squared minus U squared. Let's make a substitution based on how we've defined A and U. So the square root of A squared minus U squared is equal to the square root of A squared minus, I'm going to substitute A sine theta in for the U. So here we've got A sine theta is equal to U, so we can make a substitution there. So it's A sine theta squared. And that is equal to the square root of A squared minus A squared sine squared theta. And then I can factor out an A squared, so 1 minus sine squared theta. The square root of A squared times 1 minus sine squared theta. So if you have the square root of a real number x times a real number y, then that is equal to the square root of x times the square root of y, provided that x and y are both positive. And we are assuming that A is positive, and then our 1 minus sine squared theta is also going to be positive. We'll see why it's going to be positive here in a moment. So I can separate this. The square root of A squared is the absolute value of A, and then the square root of 1 minus sine squared theta. Let me go ahead and write this in a couple steps. 1 minus sine squared theta is equal to cosine squared theta. So we're using Pythagorean identity there. And now we have a perfect square under our square root, so we have to be careful. It's not necessarily equal to A cosine theta. It could be equal to negative A cosine theta potentially, but what we have at the bottom here is a note. What restriction should we place on theta to guarantee that U equals A sine theta is 1-to-1, basically. So for it to be 1-to-1, think about the inverse sine function. Theta needs to be defined on the interval from negative pi over 2 to positive pi over 2. And that means quadrants 1 and 4, right? These two quadrants right here. And in those two quadrants, the cosine of theta is positive. No matter which one of those two quadrants I'm in, the cosine is positive. Okay, so that allows me to drop the absolute value. And I know that A is positive as well. So this is equal to the absolute value of A cosine theta. But I can drop the absolute value and just say A cosine theta because A is positive and cosine of theta is positive. So the square root of A squared minus U squared equals A times the cosine of theta. In these trig substitution problems, what we're going to see is an integral that involves some sort of expression that looks like this. And we are going to substitute A cosine theta in place of the square root of A squared minus U squared. That's where we're going with this. Right now we're just developing why we use A cosine theta as a substitution for the square root of A squared minus U squared. Here we're going to use a trigonometric substitution to simplify each of the following expressions, and we will assume that we are working on the interval for theta between negative pi over 2 and positive pi over 2. So we're trying to think of these expressions as being of the form square root of A squared minus U squared, where the A would be the constant and U would be some expression involving a variable, so that we can use the substitution that we just came up with over here. If we have something in the form of square root of A squared minus U squared, we're going to replace that with a cosine theta. So for this first example, we can think of a as being equal to 2 and the u equal to x. And then we have something in the form of the square root of a squared minus u squared. So our substitution in general is going to be u equals a times the sine of theta. So here u is x, a is 2, and we can make that substitution. Now you can go straight to the answer because you know what the substitution is going to be, but let's see how that works exactly. The square root of 4 minus x squared. So I want to substitute in something for x squared. I've already said that x is equal to 2 sine theta, and if I square both sides, I get x squared equals 4 sine squared theta. So I'm going to substitute that in for the x squared, 4 sine squared theta, which is equal to the square root of 4 times 1 minus sine squared theta. And we'll use a trig identity there. That's equal to 2, I'm taking the square root of 4, times the square root of cosine squared theta. The square root of cosine squared theta is equal to the absolute value of cosine theta, but since we're working on the interval from negative pi over 2 to pi over 2, cosine theta is a positive value, so we can just drop the absolute value and say 2 cosine theta. Okay, so it just simplifies to 2 cosine theta. How is this helpful? Well, if we wanted to integrate the square root of 4 minus x squared dx, we might be able to use this to help us rewrite the integral in a different form where it's easier to solve. That's exactly where we're heading with this. Okay, number 2. Here we want to think of the 1 as the a and the 4x squared as the u squared, so u equals 2x. Okay, and our basic setup, we have u equals a times the sine of theta. So 2x equals 1 times the sine of theta. And we're just going to rewrite the square root of 1 minus 4x squared using this substitution. 2x equals sine theta. So that's going to be the square root of 1 minus. Now I need to substitute something in for 4x squared. So I can see right here, if I square both sides, I get 4x squared equals sine squared theta. So we're substituting in sine squared theta for the 4x squared, which is equal to the square root of cosine squared theta, which is equal to cosine theta, since we're working on the interval from negative pi over 2 to pi over 2. So that one just simplifies to cosine theta. And the last example here, we let a equal 4. We let u equal 3x. Now we have something in the form of square root a squared minus u squared. Okay, so u equals a times the sine of theta is how we're setting this up. So 3x equals 4 times the sine of theta. And if I square both sides there, I'm going to get 9x squared equals 16 sine squared theta. And I could even keep going here and say I'm going to do 16 minus 9x squared on the left, and then 16 minus 16 sine squared theta on the right, and then take the square root of both sides. So that square root of 16 minus 9x squared equals the square root of 16 times 1 minus sine squared theta equals 4 times the square root of cosine squared theta equals 4 cosine theta. So that's how it's going to simplify, 4 cosine theta. Now let's think about this right triangle. The u and the a we've reconfigured the picture here. So now a is not the hypotenuse. A is the length of the adjacent leg to the angle theta. And the hypotenuse is the side that is unknown here. Oh, I didn't go back. Let's go back to the other diagram because I didn't solve for the question mark here. Right? We can use Pythagorean theorem to solve for the length of this missing side. It's going to be the square root of hypotenuse squared minus leg squared. So that's the connection that we were making here. So in this triangle, if we use Pythagorean theorem, the hypotenuse is the square root of leg squared plus leg squared. Okay, so we're going to use this substitution that we're about to make whenever we have something in the form of square root of a squared plus u squared. In this case, u over a equals the tangent of theta. Tangent of theta. Multiplying both sides by a, we get u equals a tan theta. And then the square root of a squared plus u squared would be the square root of a squared plus a squared tan squared theta. Factor out in a squared times 1 plus tan squared theta. 1 plus tan squared theta equals secant squared theta. And that is a perfect square, so if we take the square root, we're going to get a times secant theta absolute value. But a is positive, so we're making that assumption here. A is positive, and we're going to place a restriction on theta to guarantee that the secant of theta is positive. So what restriction on theta guarantees that a tan theta, u equals a tan theta, is 1 to 1? So if we think about the arctangent function, that is defined from negative pi over 2 to positive pi over 2, just like arcsine. So we're going to place that same restriction there, which means we are working in quadrants 1 and 4, and secant is the reciprocal of cosine, so it is positive in those two quadrants. So we can just say a secant theta. So that's the substitution we're going to make. When we have something in the form of a squared plus u squared, we can replace it with a secant theta. Okay, so let's try it here. These look like the same expressions. So we've got a equals 2, u equals x. Here we've got a equals 1, u equals 2x. Here we've got a equals 4, u equals 3x. And we're making the substitution a secant theta. So you could just go right straight to the answer if you see how this is going to work out. Otherwise, we're going to use u equals a tan theta as our substitution, and u equals x in this first one, and a equals 2. And if I square both sides, I get x squared equals 4 tan squared theta. So the square root of 4 plus x squared equals the square root of 4 plus 4 tan squared theta equals the square root of 4 times 1 plus tan squared theta. 1 plus tan squared theta equals secant squared theta. And since we are working on the interval from negative pi over 2 to pi over 2, this is going to equal 2 secant theta, okay, for number 1. Number 2, again, it's u equals a tan theta. So 2x equals 1 times tan theta. If I square both sides, 4x squared equals tan squared theta. And then I'll make a substitution. The square root of 1 plus 4x squared equals the square root of 1 plus tan squared theta equals the square root of secant squared theta equals secant theta, since we are working on the interval from negative pi over 2 to pi over 2. Okay, and then the last one. Again, it's u equals a tan theta. That's the substitution we're going to make. So 3x equals 4 tan theta. Square both sides. 9x squared equals 16 tan theta. So the square root of 16 plus 9x squared equals the square root of 16 plus 16 tan, oh, I forgot my square there, tan square theta equals the square root of 16 times 1 plus tan squared theta equals the square root of 16 times secant squared theta equals 4 secant theta. Okay, so we're going to use this substitution, u equals a tan theta, when we have an expression in this form up here, square root of a squared plus u squared. All right, one more scenario here. Now again, we've rearranged or relabeled the sides of the triangle. So now U is the hypotenuse and A is the leg adjacent to theta. So U over A, hypotenuse over adjacent, not adjacent over hypotenuse. Adjacent over hypotenuse is cosine, but this is hypotenuse over adjacent. So it's the reciprocal of cosine, which is secant theta. Multiply both sides by A, U equals A secant theta. And then the square root of U squared minus A squared, well, U squared would be A squared secant squared theta minus A squared, factor out an A. Use one of our Pythagorean identities there. Secant squared theta minus 1 equals tangent squared theta. And the square root will equal a tan theta, absolute value. So what restriction are we going to place on theta? We already have that A is positive, so that's going to allow us to drop the absolute value around the A. And then for secant to be 1-to-1, think about the arc cosine function. That's between 0 and pi. But since this is secant, the reciprocal, and we can't have 0 in the denominator, secant is undefined at pi over 2, we actually have to break that up. It's going to go from 0 to pi over 2, including the 0, not including the pi over 2, because secant is not undefined at theta equals 0, but it is undefined at pi over 2, and then pi over 2 to pi, like so. So that is quadrants 1 and 2. And in quadrants 1 and 2, tangent is not always positive or always negative. It depends. So this one ends up being piecewise. It's either equal to negative a tan theta or a tan theta, depending on which quadrant we're in. So we know A is positive already. Tangent is positive in quadrant 1. So this would be a tan theta for quadrant 1. So let me put the negative on the lower branch. Like that. So we can say this is for angles between 0 and pi over 2. And then from pi over 2, not including theta, to pi, we're in quadrant 2, and if we want to drop the absolute value, it would be negative a tan theta. So this is the substitution we're going to make if we have something in the form of, let's solve for a question mark here. Using Pythagorean theorem, the length of that leg is the square root of hypotenuse squared minus leg squared. Okay, so when it was the square root of a squared minus u squared, we used a sine substitution. When it was the square root of a squared plus u squared, we used a tangent substitution. And here, when it's the square root of u squared minus a squared, a being the constant, we're going to use a secant substitution. All right, so we've got u equals x, a equals 2. Here, u equals 2x, a equals 1, u equals 3x, a equals 4. And in each one of these cases, we have the form u squared minus a squared. So our substitution is going to be u equals a secant theta. U equals a secant theta. U equals a secant theta. So x equals 2 secant theta here. And then I can square both sides. I usually just go ahead and do that here. X squared equals 4 secant squared theta. So the square root of x squared minus 4 becomes the square root of, now make a substitution for x squared, 4 secant squared theta minus 4. Factor out the 4, theta minus 1. This identity, I always have to sort of say this in my head, tangent squared theta plus 1, because that's how I memorized it, equals secant squared theta. So secant squared theta minus 1 is equal to tangent squared theta. So this is equal to the square root of 4 tan squared theta. So it's 2 tan theta, or possibly negative 2 tan theta. It's 2 tan theta in quadrant 1, but it's negative 2 tan theta in quadrant 2. But we do have this assumption that we're making here, that we are working in quadrant 1. Okay, for number 2, we have now 2x equals 1 times secant theta. If we square both sides, we'll see 4x squared equals secant squared theta. So the expression square root of 4x squared minus 1 becomes, we're going to substitute in for the 4x squared, secant squared theta minus 1, and that turns into square root of tan squared theta, which just becomes tan theta. Okay, and number 3, u is 3x, a is 4, so we have 3x equals 4 secant theta. The square root of 9x squared minus 16. Let's square both sides here. We get 9x squared equals 16 secant squared theta. And we'll make our substitution. So the square root of 9x squared gets replaced with 16 secant squared theta minus 16. And then factor out the 16. Secant squared theta minus 1 becomes tan squared theta. So 4 tan theta would be that substitution. All right, so here in summary is the substitution we're going to make when we're working with expressions of this certain form. If we see the square root of a squared minus u squared in our integral, we can try making the substitution u equals a sine theta, and then we'll just use this condition that we're working on the interval from negative pi over 2 to pi over 2. Now, typically when we make a substitution like this, we're going to substitute in something involving theta into the problem, and then at the end, we will do a reverse substitution to get the theta out of the problem. So you don't have to worry too much about this interval over here. You don't even really need to show that while you're working, because we're going to, like I said, unsubstitute the theta out of the problem in the end. All right, and then if we have an expression that involves the square root of a squared plus u squared, we're going to make the substitution u equals a tan theta. And if we are working with the square root of u squared minus a squared, we are going to make the substitution u equals a secant theta. Which of the following substitutions should we make to evaluate the following integral? Here we've got 9 is a constant, so that's the a squared. And then the variable x squared is the u squared. So we have the square root of a squared minus u squared. When you have that form, you're going to make a sign substitution. And the way that I remember this is that the derivative of arc sine x is 1 over the square root of 1 minus x squared. And so like that I just have memorized already. And I know that's in the form of the constant squared minus the variable squared. So that's how I associate that with sine. So when I see constant squared minus variable squared, I immediately just think of the sine function. So the substitution we're making there is u equals a sine theta. The a equals 3 and the u equals x. So x equals 3 sine theta. Now there are other things in this integral, right? There's an x squared here, and there's a dx here. And this is just like a u substitution problem. In u substitution, you rewrite the integral so it only has u's in it. You get all the x's out, you rewrite everything in terms of u. Well, in these problems, we're writing everything in terms of theta. So yes, we are also going to have to get rid of that extra x squared, and we're going to have to get rid of the dx. We're going to have to somehow substitute something in for that in terms of theta. Okay, so let's work this one all the way out. We are trying to integrate 1 over x squared times the square root of 9 minus x squared dx. Now, anytime you're looking at an integral, you should always ask yourself first, can I do this using u substitution? Because u substitution will be much easier than trig substitution. But we cannot use u substitution here, or maybe you can, but it's not going to work out very easily because of that x squared in the denominator. So I'm going to make a trig substitution, noticing again that this is in the form of the square root of a squared minus u squared. So immediately I think to use a sine substitution. U is x, a is 3, so my substitution becomes x equals 3 sine theta. That's going to allow me to substitute in here, and to make a substitution for dx, I need an equation that relates dx and d theta, because I'm turning this into an integral in terms of theta. So just like we do with u substitution, we're going to take the derivative. Once we have this equation that relates our two variables, in u substitution, you're relating the u and the x. In this case, we're relating x and theta. Okay, so once we have that equation that relates x and theta, we can take the derivative, and that's going to give us an equation that relates dx and d theta. So we can make another substitution there. So I'm just taking the derivative of the left. The derivative of x is dx. On the right, the derivative of 3 sine theta is 3 cosine theta d theta. So technically, the derivative of x with respect to theta is like this, dx over d theta. And I'm just moving the d theta over to the right-hand side. Okay, so this is what dx is equal to. So I'm going to make a substitution. 3 cosine theta d theta is equal to dx. So we're going to substitute it in for the dx. And then x equals 3 sine theta, so I can substitute 3 sine theta in for the x, but I normally find it easier to do a little of the algebra work outside of the integral. And by that, I mean I'm going to square both sides of that equation. So I'll have, so I'm going to put over here, x squared equals, I'm looking here, I'm squaring both sides of that equation. X squared equals 9 sine squared theta. Now you can do some more with that. You can do 9 minus on both sides if you want to go ahead and work that out here outside of the integral, or you can go ahead and substitute in now the 9 sine squared theta for the x squared. I'm going to go ahead and, just to be super clear what we're doing here, draw an arrow like I did for the dx substitution. So this is going to get substituted in for the x squared. And then whatever you still have left over, you need to make a substitution for that as well. So it's also going to get substituted in for that x squared right there. And at that point, we should only have thetas in the problem. Okay, so this becomes integral 1 over. The x squared is getting replaced with 9 sine squared theta. Then we have the square root of 9 minus, and I'm replacing the x squared with 9 sine squared theta. Then we're replacing the dx. Do not forget to sub in for the dx. I'm replacing the dx with 3 cosine theta d theta. And now we have a new integral that's written just in terms of theta. So let's simplify where we can. The square root of 9 minus 9 sine squared theta, factor out the 9, then you'll have, I'm just going to do this and then erase it, 9 times 1 minus sine squared theta, right? This is what we were practicing earlier. It's become 9 times cosine squared theta, and then you take the square root and you get 3 cosine theta. Okay, so that whole square root right there just turns into 3 cosine squared theta. So 1 over 9 sine squared theta, 3 cosine theta, times 3 cosine theta d theta. And now we can eliminate that common factor. And this is 1 over 9 sine squared theta d theta. Okay, we're going to keep going because we don't know how to integrate 1 over sine squared theta. So we just keep simplifying. 1 over sine theta is cosecant theta. So 1 over sine squared theta is cosecant squared theta. 1 over 9 is a constant multiple. So I can bring that outside of my integral. And this becomes 1 over 9 times the integral of cosecant squared theta d theta. That is an integral that we can do by recognition. The derivative of tangent theta is secant squared theta. The derivative of cotangent theta is negative cosecant squared theta. So this is negative 1/9 cotangent of theta. That's the answer to this integral in terms of theta, but we need to write our final answer in terms of x. So now we need to do a reverse substitution. What can I substitute in for theta, or what can I substitute in for the cotangent of theta so I can get back to my original variable x? So at this stage, when you need to do the reverse substitution, I don't recommend trying to solve for theta. I recommend just drawing yourself a right triangle so you understand the relationship between x and theta here. Go ahead and label your angle theta, and then look at your substitution that you originally made. The original substitution will tell you how x is related to theta in the right triangle. If x equals 3 sine theta, divide both sides by 3 there. You get sine of theta equals x over 3. If the sine of theta equals x over 3, the x must go here and the 3 must go here, because the sine of theta is defined in a right triangle as the opposite length over the hypotenuse. Okay, so again, I just don't know where's a good place to write it on here. If you divide both sides by 3 here, you get x over 3 equals sine theta. And sine is opposite over hypotenuse, so label the opposite leg x and the hypotenuse 3. Then use the Pythagorean theorem to get the missing side. So the leg here is the square root of hypotenuse squared minus leg squared. And this expression that you're writing on the third side should match this thing in your integral here, the substitution that you originally tried to make, or the reason that we're doing trig sub there. Now I can just read from the picture what is the cotangent of theta and get my final answer. So negative 1/9. The cotangent of theta is adjacent over opposite. So times square root of 9 minus x squared over the opposite is x, okay, plus c. So that will be my final answer. So we were able to take an integral that we don't know how to solve in terms of x. Use substitution is not going to work. Integration by parts is not going to work. We don't have a way to solve that integral as is. But by making this substitution and using trigonometric properties, we can write it in a much simpler form. I mean, you might not think it's simpler, but in a form at least that we know how to integrate and get our final answer. Next example, which of the following substitutions should we make if we want to integrate 1 over the square root of 4x squared plus 1? So looking at this is in the form of square root of u squared plus a squared. Now addition is commutative, so when we looked at the substitution, we had a squared plus u squared. That's fine. We want to make a tangent substitution here. And the reason, or the way that I remember its tangent, is also involving the inverse tangent function. If I think about the derivative of inverse tangent, it's 1 over 1 plus x squared. It's in the form of a squared plus u squared, or x squared, or whichever way you want to think about it. So we're going to make a tangent substitution. We're going to use u equals a tan theta. The u is 2x. The a is 1. So 2x equals tan theta. That's the substitution we're going to want to make. So here we are, 2x equals tan theta. That's going to allow us to substitute, well, I would say we should take this, we should square both sides. So 4x squared equals tan squared theta. And then that's going to allow us to make a substitution here for the 4x squared. We can replace it with tan squared theta. Or, again, if you want to do some more work outside of the integral, we can add 1 to both sides of this equation and say 1 plus 4x squared equals 1 plus tan squared theta. equals secant squared theta. And now we can just say, okay, I'm going to substitute 1 plus 4x squared for secant squared theta. You can even go further with that, right? You can say the square root of this, the square root of this equals the square root of this equals the square root of this equals secant theta. Again, we're not worried about what quadrant we're working in because we're going to do a reverse substitution in the end. So now you could just say, well, I'm going to replace this entire thing, square root of 1 plus 4x squared, with secant theta. So we have a plan for the square root of 4x squared plus 1. That's going to get replaced with secant theta. We also must substitute something in for dx. So what does dx equal? Take the derivative of both sides of this equation. Go back to the original equation that relates x and theta. Take the derivative. Okay, so on the left, the derivative of 2x is 2 dx over d theta, but I'll put the d theta on the right. The derivative of tan theta is secant squared theta d theta. So dx equals 1/2 secant squared theta d theta. That's what we're going to substitute in for the dx. And our integral becomes 1 over secant theta times 1/2, we'll bring out the constant multiple, secant squared theta d theta. And let's simplify some more. So that's just 1/2 times secant theta d theta. Okay, so that looks about as simplified as it's going to get, right? We're just integrating secant theta. How do we integrate secant theta? This is actually much more difficult than it looks. Integrating secant theta. We can't use, it's not a recognition one unless you just happen to know the derivative of what equals secant theta. We can't use a u substitution. I don't know if we could use integration by parts, but we're going to use a trig identity to write this in a different way. And this is not something that you would probably think to do on your own. So I'm just going to show you. We're going to manipulate this using a trig identity to get it into a form where we can just make some more substitutions. So I'm going to take secant theta and I'm going to multiply it by something over something. So I'm just multiplying by a fancy form of 1. I'm going to multiply it by secant theta plus tangent theta over secant theta plus tangent theta. You'll see why I'm doing this here very shortly. When we multiply out the numerator, we have secant squared theta, which is easy to integrate, plus secant theta tangent theta, which is also easy to integrate. Those are both recognition, over secant theta plus tan theta d theta. But we also have something else very convenient happening here. Think about the derivative of the denominator. What's the derivative of secant theta plus tangent theta? Well, the derivative of secant theta is secant theta tangent theta, and the derivative of tangent theta is secant squared theta. So the derivative of the denominator is the numerator. How do you integrate something in this form? 1/2 integral f prime of x over f of x dx. How would you integrate that? That is just a straight up u substitution. If u equals f of x, du equals f prime of x dx, and that's exactly what we have here, so it's just 1 over u du, 1/2 integral 1 over u du, which is 1/2 ln absolute value of u plus c. Okay, so the u in our case is secant theta plus tangent theta, and the answer 1/2. Oh wait, we've got an x. Where did that 1/2 come? I'm wondering where this 1/2 came from. Did I bring it over just because I saw the 1/2 right here? Where did that 1/2 come from? I think so. we don't need an extra 1/2. Okay, so 1/2 ln absolute value, and the u was the secant theta plus tangent theta, and then plus c. Okay, so that was a bit difficult, and you get to this point and you are probably just glad you got an answer, but remember that's not our final answer because we need an answer in terms of x, and this answer is still written in terms of theta. So I am now going to draw my right triangle, label one of the angles theta. I'm going to look at my original substitution equation to see how to label the sides of my triangle. If 2x equals tan theta, then I'm going to think of tan theta as 2x over 1. 2x over 1. Theta, or tangent theta, is opposite over adjacent. So 2x over 1, and then the hypotenuse would be the square root of leg squared plus leg squared, which does always do a quick check and make sure it matches where we started. Okay, so now I can just read the values of secant theta and tan theta from the triangle. So this is equal to 1/2 ln absolute value. Secant theta, if cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent, plus, and then tangent is opposite over adjacent, plus c. So that is our final answer here. 1/2 ln absolute value, square root 1 plus 4x squared plus 2x plus c. Which of the following substitutions should we make if we want to integrate 1 over x squared plus 1 to the 3/2? So this looks a little different because we're not seeing the square root. But when you think about rational exponents, 3 over 2 means you're raising to the power 3 and then you're taking the square root. So it does still involve a square root. And you don't have to have the square root in order to try trigonometric substitution. Really, if you just have the u squared plus a squared, or the u squared minus a squared, or the a squared minus u squared, that's the important part that signifies that you might be able to do this using trigonometric substitution. So this is going to be a tangent substitution. It's in the form of u squared plus a squared. So we're doing a tangent substitution. U equals a tan theta. The u is equal to x, the a is equal to 1. So just x equals tan theta is the substitution we should make here. X equals tan theta. So I'm going to go ahead and square both sides of that equation. X squared equals tangent squared theta. And I'm trying to substitute it in here, but I might as well just substitute the whole x squared plus 1. So I'll add 1 to both sides. X squared plus 1 equals tan squared theta plus 1. And then if I want to, I can just go ahead right now and raise both sides to the power 3/2 here. And tangent squared theta plus 1 is equal to secant squared theta. So secant squared theta to the power 3/2. So I'm taking secant theta, I'm raising it to the power 2, and then raising it to the power 3/2. So you can multiply your exponents. That's secant theta cubed. Secant cubed theta. Secant cubed theta. So that entire denominator is going to get replaced with secant cubed theta, because that is what x squared plus 1 to the 3/2 is equal to. And for the dx, we're going to look at this original equation, take the derivative of both sides. So dx equals, derivative of tan theta is secant squared theta d theta. So that is going to be substituted in for dx. And now we're going to rewrite the integral. We've got 1 over secant cubed theta, secant squared theta d theta. Simplifying, we have 1 over secant theta d theta. which is cosine theta d theta. We know how to integrate cosine theta. That's just sine theta. And we're going to draw a right triangle so we can get our answer back in terms of x theta. So looking here, tangent theta equals x over 1. X over 1. So that's the square root of 1 plus x squared. Sine of theta equals opposite over hypotenuse. And then plus c. So x over the square root of 1 plus x squared plus c. Next, which substitution should be made if we want to integrate the square root of x squared minus 3 over x from root 3 to 2? So you might think u substitution here if we let u equal x squared minus 3. The problem is this x is in the denominator, so it's not going to help us get what we need for the du. So we're looking at the numerator as something in the form of square root u squared minus a squared. Okay, and that is a secant substitution. We want u equals a secant theta. The u is x. The a squared equals 3. If a squared equals 3, then a equals root 3. So root 3 secant theta, that's the substitution we want to make. X equals root 3 secant theta. So I'll square both sides. X squared equals 3 secant squared theta. Then I'm going to subtract 3. So x squared equals 3 secant squared theta minus 3. Oh, I didn't subtract 3 on the left. Sorry. X squared minus 3 equals 3 secant squared theta minus 3. Then we can factor out a 3. And secant squared theta minus 1 equals tan squared theta. So we have x squared minus 3 equals 3 tan squared theta. Now I can take the square root, and I get square root of x squared minus 3 equals square root of 3 tan theta. Okay, so I'm going to substitute that in for the square root of x squared minus 3. So we've got integral. Now because I'm making a substitution, the root 3 and the 2 are no longer going to be my bounds because those are x values. So I'm just going to put placeholders here, alpha, beta, so I don't have to convert them in terms of theta. So we've got root 3 tan theta over x, and for x I'm going to substitute in root 3 secant theta. And for dx, I haven't done that part yet, I'm going to take the derivative of both sides of this equation. So dx equals root 3, the derivative of secant theta is secant theta tangent theta d theta. Okay, root 3 secant theta tan theta d theta. And then we'll simplify. So we have a common factor of root 3 and secant theta. And we are left with integral from alpha to beta. Root 3 is a constant multiple. I'll bring out tan theta times tan theta, so tan squared theta d theta. How do we integrate tan squared theta? Well, we can use a trig identity. Tangent squared theta equals secant squared theta minus 1. And secant squared theta, you can integrate by recognition. The derivative of tan theta is secant squared theta. And then 1 you can integrate by recognition. So root 3 tan theta minus theta. We're taking the integral with respect to theta. So the integral of 1 is theta. From alpha to beta. So at this point, we are either going to have to convert the x equals 2 and x equals root 3 in terms of theta, or go back in terms of x let's just go ahead and go back in terms of x. So I'm going to make a triangle. It's actually not easier to go back in terms of x. I think it's the same amount of work either way. So it's completely up to you which way to do it. So I'm going to look back at my original substitution to label my triangle. Secant theta equals x over root 3. If we divide both sides of that equation I just highlighted by root 3, we get secant equals x over root 3, and that means cosine theta equals root 3 over x. And cosine is adjacent over hypotenuse. And then the third side, using Pythagorean theorem, that's the square root of hypotenuse squared minus leg squared. So making our reverse substitution, the tangent of theta is the square root of x squared minus 3 over square root of 3 minus, now what about theta? Because this isn't sine theta or cosine theta or tangent theta, secant, cosecant, cotangent. It's just theta, So we're going to have to use an inverse trig function to define theta in terms of x. You can take your pick. Since we did an original substitution of secant, I don't really want to use arc secant, but I'll use arc cosine. So we know the cosine of theta equals root 3 over x. So we can say that theta equals arc cosine, or cosine inverse, root 3 over x. And then we're evaluating from root 3 to 2. I'll just set that guy aside. Okay, so I could do some simplifying here, but I don't think I'm going to. Just going to go ahead and sub in the upper limit of integration, which is 2. So 2 squared is 4, minus 3 is 1, square root of 1 is 1, so 1 over root 3, minus the arc cosine of root 3 over 2. Where does cosine equal root 3 over 2? 30 degrees, pi over 6. Now we substitute in the lower bound. Root 3 squared is 3, minus 3 is 0. Okay, so that's just 0. Minus arc cosine of root 3 over 3. The arc cosine of 1, where does cosine equal 1? 0. So my final answer is root 3. I'm going to just go ahead and, since it does simplify nicely in that first term, I'll go ahead and distribute the root 3. So it's 1 minus root 3 over 6 times pi for the final answer. And our final example, we want to integrate x over the square root of 3 minus 2x minus x squared. You could try u substitution here, but your du, if you're letting what's inside of the radical be your u, your du is going to be negative 2 minus 2x. And so you'll have to do some algebraic manipulation to get what you need for your du. It might work. I'm not saying it won't work, but we're going to try this using trig substitution. So we're going to complete the square in the denominator because right now we don't have something in the form of u squared minus a squared minus u squared, or a squared plus u squared. So we're going to complete the square here. 3 minus 2x plus x squared. I think that's going to be the easiest way to complete the square, is if we write it like this. Let me just redistribute that and make sure that's right. 3 minus 2x minus x squared. Okay, so 3 minus x squared plus 2x. 3 minus x plus 1 squared. And now I'll see how to adjust this. So if I were to multiply this all back out, I'd have x squared plus 2x plus 1 times negative 1, and then 3. So I'd have 3 minus x squared minus 2x minus 1, so I need to add 1. Plus 1. So it's 4 minus x plus 1 squared. That's what we get when we complete the square. This is equal to the integral of x over the square root of 4 minus x plus 1 squared dx. Now we have something in the form of a squared minus u squared. Okay, so we're going to make a sine substitution. U equals a sine theta. The u is x plus 1. The a is 2. If I square both sides, I get x plus 1 squared equals 2 cosine theta. What am I doing? Sorry, I'm mixing up steps. If I square both sides, I get x plus 1 squared equals 4 sine squared theta. I'm just used to taking the derivative as the second step. Oops. We do need to take the derivative of this equation right here. And that's going to give us the derivative of x plus 1 is dx. The derivative of 2 sine theta is 2 cosine theta d theta. Okay, so I'm going to make some substitutions. I'm going to replace 4 sine squared theta for the x plus 1 squared. And you could work some more with that. I like to work with it outside of the integral. I like to continue to simplify. So let's just, oops, too much. Let's move him down here. That's our derivative. And I'm going to do 4 minus on both sides of this equation, because I'm trying to get a perfect match with what I have over here. 4 minus 4 sine squared theta equals 4 times 1 minus sine squared theta equals 4 times cosine squared theta. And that's all under a square root. So we're going to do square root equals 2 cosine theta. Okay, so now I can say 2 cosine squared theta is going to replace all of that. So all of that becomes 2 cosine theta. And then this 2 cosine theta d theta replaces the dx. Okay, so we have integral of x over 2 cosine theta, 2 cosine theta d theta. And I have to get rid of the x. So I can come back here and say x equals 2 sine theta minus 1. 2 sine theta minus 1. And I can see right away that this is going to cancel out. So let me write that a little neater. 2 sine theta minus 1 d theta. And we're ready to integrate that. The integral of 2 sine theta is negative 2 cosine theta. And the integral of minus 1 is minus theta plus c. Now we have to write our answer in terms of x. So I'm going to draw a right triangle. Go to the original substitution equation. Here, nope, not that one. Here, if you solve that for sine theta, you get sine theta equals x plus 1 over 2. Opposite over hypotenuse. And then the missing side is the square root of hypotenuse squared minus leg squared, which does in fact match what we have in our radical there. Okay, so negative 2, the cosine of theta is square root 4 minus x plus 1 squared over 2 minus, now we've got just theta again, so we have to use one of our inverse trig functions. You can decide which one you want to use. Typically, if I start with a sine substitution, I go with arcsine, but you don't have to do that. So minus arcsine, and the arcsine of theta, I'm going with opposite over hypotenuse, x plus 1 over 2, plus c. Okay, so that will be my final answer. All right, so trigonometric substitution, again, is just sort of a fancy form of u substitution. We're just substituting in terms of theta instead of in terms of u. Just takes a little practice, and you do have to know your trig identities. So if you haven't reviewed trig identities in a while, it'd be a good time to make yourself a little formula sheet with the most important trig identities. You can see from the examples that we've done, the Pythagorean identities are ones we're using a lot. Reciprocal identities are ones we're using a lot, and then we're also working with our inverse trig functions. This tends to be one of students' least favorite lessons in AP Calculus BC, but I think it's really cool that we can start with an integral that we have no idea how to integrate, and just by rewriting it in terms of our trig functions, turn it into something that is much more manageable. Thanks for joining. I'll see you guys next time.